Good day. Now let's proceed to chapter 22, Gauss's Law. We will be answering problem numbers 22.23, 22.33, and 22.41. So let's have the problem. Problem 22.23. An electron is released from rest at a distance of 0.3 meters from a large insulating sheet of charge that has a uniform surface density or charge density of positive 2.9 times 10 to the negative 12 coulomb per square meter. Part A. How much work is done on the electron by the electric field of the sheet as the electron moves from this initial position to a point of 0.05 meter from the sheet? Part B. What is the speed of the electron when it is this far from the sheet? To better illustrate the problem, this is the initial position of the electron and it moves towards the sheet and its distance is 0.05 meter. We will use these constants, the Coulomb's constant, the magnitude of the electron's charge, the mass of the electron, and the permittivity of free space. The electric field at any point of an infinite sheet of charge with a uniform charge per unit area sigma is given by this formula. Electric field is equal to sigma over 2 epsilon naught. Substituting the values, we have the surface charge density here and the epsilon naught. This will give us 0.1638 Newton per Coulomb. Determining the electric force, so we have this formula. The electric force is equal to the product of the charge and the electric field. Our charge is this and the electric field value is this. And multiplying these two, we have 2.624 times 10 to the negative 20 Newton. Now, finding the work done on the electron by the electric field. So work is equal to the force times the distance. The distance traveled by the electron is from this point up to this point. So that is 0.25 meter. So substituting the values, so we have the force and the distance, giving us 6.56 times 10 to the negative 21 joules of work. Now, for part B, in solving the speed of the electron, using work energy theorem, we know that the total work is equal to the change in kinetic energy. So, final kinetic energy minus initial kinetic energy. Since the electron is at rest, so that is the initial condition, therefore the velocity is 0, giving us the initial kinetic energy of 0, leaving us with the kinetic energy final, which is 1/2 mv sub 2 squared is equal to the work. Rearranging this equation to get the velocity of the electron, we have v sub 2 is equal to square root of 2w over m. Substituting the values, we have this work done on the electron by the field and the mass of the electron, giving us 1.2 times 10 to the 5 meter per second. So this is the speed of our electron. Problem 22.33. A small sphere here with a mass of 4 times 10 to the negative 6 kilogram and a charge of 5 times 10 to the negative 8 coulomb hangs from a thread near a very large charged insulating sheet. The charge density on the surface of the sheet is uniform and equal to negative 2.5 times 10 to the negative 9 coulomb per square meter. Find the angle of the thread. To solve this, let's have the force diagram. So the forces acting on the ball are the tension, the electric force, and the weight. The tension has two components, the X component and the Y component. We will also use the permittivity of free space. The forces on the ball, which are gravity, tension, and electric force due to the field, add to 0 since the ball is suspended or at rest. Since the ball is in equilibrium, then the summation of the forces along X and along Y are 0. So let's solve for the x component. So as seen in this diagram, we have positive t sine theta and negative electric force because it is to the left. Rearranging this equation, we have t sine theta is equal to the electric force. Now let's proceed with the y component. As seen in this diagram, we have positive t cos theta, the y component of the tension, and the weight, which is negative because it is downward, so minus mg. Rearranging this, we have t is equal to the weight divided by cosine theta. Now, substituting t with this value of t, we have mg sine theta over cosine theta is equal to the electric force. So we have sine theta over cosine theta here. And since this electric force is equal to the product of the electric field and the charge, we have tan theta, which is sine theta over cosine theta, is equal to the charge multiplied by the electric field divided by the weight, or mg. Rearranging this to get the angle of the thread, we have arctan QE over mg. So we have the value for Q, we have the value for M and G. We don't have the value for E. So let's solve for the electric field. So the electric field at any point of an infinite sheet of a charge with a uniform charge per unit area sigma, is given by this formula. Electric field is equal to sigma over 2 epsilon naught. Substituting the values, this is our surface charge density and the epsilon naught, giving us 1.41 times 10 to the 2 Newton per coulomb. Solving for the angle, we will use this formula, and substituting the values, we have the charge of the small sphere, the electric field here, the mass of the small sphere, and the acceleration due to gravity. And this will give us 10.2 degrees. So this angle is 10.2 degrees. Problem 22.41. A very long solid cylinder with radius big R has positive charge uniformly distributed throughout it, with charge per unit volume ρ. Derive the expression for the electric field inside the volume at a distance small r from the axis of the cylinder in terms of the charge density ρ. What is the electric field at a point outside the volume in terms of a charge per unit length lambda in the cylinder? Compare the answers to parts A and B for small r is equal to big R. Then graph the electric field magnitude as a function of small r from small r is equal to 0 to small r is equal to 3 big R. So this is the figure for the problem. So to solve this, we will enclose the solid cylinder with a Gaussian cylinder or imaginary cylinder, and the solid cylinder has the radius of big R while the Gaussian cylinder has a radius of small r. The length of the Gaussian cylinder is L. The volume of the Gaussian cylinder, which is in color blue, is pi small r squared L. The area of its curved surface is 2 pi small r L. The charge on the length L of the charge distribution is Q is equal to lambda L, where lambda is equal to rho pi big R squared. Now let's have the electric field inside, where the small r is less than the big R. So the electric field inside must be in terms of the volume charge density rho. So the Q enclosed, or the charge enclosed by the Gaussian surface, is rho pi small r squared L. By Gauss's law, we have this formula. So the electric flux is equal to the electric field multiplied by the area, and it is equal to the Q enclosed over epsilon naught. So this is our Q enclosed. So let's substitute the value to this. And our area is 2 pi small r L. So we will cancel pi to the left side and to the right side, as well as the r and the L. This will give us, rearranging this equation, when we cancel these variables, we will have electric field is equal to rho small r over 2 epsilon naught. And the electric field is radially outward because our solid cylinder has a positive charge which is uniformly distributed throughout it. Now, after solving the electric field inside, let's solve for the electric field outside, wherein the small r is greater than the big R. Now, this time, in terms of linear charge density, lambda. The Q enclosed is equal to lambda L is equal to rho pi big R squared L. We will use Gauss's law again, and substituting the value, our area is 2 pi small r L and is equal to the Q enclosed. So the Q enclosed is rho pi big R squared L, as you can see here. We will cancel pi, we will cancel the length. So rearranging this equation, we will have electric field is equal to rho pi, by the way, rho big R squared over 2 epsilon naught small r. Now, since the problem requires us to solve the electric field outside in terms of linear charge density lambda, so we will substitute the value. So since lambda is equal to rho pi big R squared L, we will get this expression. We will substitute rho here, and we will get this expression. Now, the electric field is radially outward. As we said before, the charge of the solid cylinder is positive and it is uniformly distributed throughout it. Now, for part C, compare the answers to part A and B. So that is this. For small r is equal to big R. So comparing the two, so this is the electric field inside and this is the electric field outside. And we will substitute r, small r is equal to big R. So when we substitute this r with big R, so we will get this. And if we will substitute small r, small r with big R, so we will get this. So they are the same. They have the same electric field. For the last part, we are to graph the electric field magnitude as a function of r from r is equal to 0, small r is equal to 0, to r is equal to 3 big R. So first, let's graph the electric field inside using this equation. So as you can see, it is directly proportional. So as the radius increases, the electric field increases proportionally. For the electric field outside, so R or small r is inversely proportional with the electric field, giving us this line. So as R increases, the E decreases.